Video number 1 for the practice test for Unit 8, Atomic Physics. Number 1, complete the following reaction. Okay, we have hydrogen 2, commonly called deuterium, and we just need to know the A, B, and XY values. So it's just a balancing. Here we have a 1 and a 1, so we have a total of 2 on this side. We have a total of 2 on this side, therefore B must be 0. 2 and 2 makes 4 on this side. We have 3 over here, so A must be 1. All right, what is X? Let's do X first because that's pretty straightforward. X has a 2 here. If it has a 2 there, it is automatically helium. So we can eliminate A and B right off the bat. Helium, now the only question is, what is this? Proton or neutron? And since the atomic number down here is 0, that means it has 0 protons, therefore it must be a neutron because it has 1 nucleon, and that nucleon is the neutron. So the answer to number 1 is, oops, I circled the wrong one, D. D as in dog. Number 2, what is the charge to mass ratio of a particle traveling at that velocity perpendicular to a magnetic field of intensity? That intensity of a circular path has that radius. So we're dealing with a charged particle in a magnetic field, and it will go in a circular path. Therefore, the magnetic force equals the centripetal force. QVB equals mv squared over r, and we want the charge to mass ratio, so we're solving for Q over m. And you probably, it's one of those formulas that's worth memorizing just because it's that important. So the charge to mass ratio equals the velocity divided by the field strength times the radius. The numbers are all there for you. You can go through the mathematics and you end up getting D, also as in dog. Just make sure you convert the centimeters to meters, and that's it. Number 3, in a Millikan oil drop experiment, which of the following forces did not factor into the design or the analysis? So if you'll recall the Millikan oil drop experiment, you take a drum here or something, a container, you put a hole in it, you charge, you charge this one, let's say negatively, and you charge this positively, then you drop oil drops through it that are charged oil drops, so you put them through a spray or something, so we'll charge them through friction, and then the ones that have gained electrons will fall. Gravity will pull them this way, but the electrostatic force will push them that way. And if they've lost electrons, so they're positively charged, well, then gravity will pull them that way, and the electrostatic force will pull them that way. The key point being, in this experiment, which of the following which of the following forces is not part of the equation or part of the design, and that would be B, the magnetic forces. There is no magnetic force here. And then we go into 4, which is an mathematical application of this. An oil drop with that mass is suspended with an electric field of that electric field strength. How many, and notice that's kilonewtons per coulomb, how many elementary charges has the oil drop gained or lost? All right, so we have, what do we have there? We have the electrostatic force equals the gravitational force. And that formula for electrostatic force in this case is EQ. The gravitational force is mg, and what are we trying to find? We're going to try to find out Q. Again, pretty straightforward. Mass is given to you, gravity 9.81, assuming you do it on Earth. The electric field strength is given to you, just remember that's in kilonewtons, so it's 3.43 times 10 to the 3. You put those numbers in and you get a Q value of 8 times 10 to the negative 19 coulombs, but we want to know how many elementary charges is that. So you're going to divide by the elementary charge for one electron and one proton is 1.6 times 10 to the negative 19. B, pretty straightforward. Moving on, number 5 says, in which device are particle tracks of subatomic particles formed by a liquid turning into a vapor? So this is just a knowledge question. It's obviously going to be a cloud chamber or a bubble chamber. Which one is it? You've just got to remember that a cloud chamber changes vapor into liquid, and a bubble chamber does the opposite, which is liquid into vapor. Answer B. Next question. In a bubble chamber within a magnetic field, the following types of tracks may be observed. A straight track. So as you recall, if it's a straight track, then that means there's going to be no charge, right? Because they won't be deflected by the magnetic field. If it's slightly curved, then it has a charge. If it's highly curved, it has a charge. And if it's a branching track, that was like one of the examples we did where a gamma ray just spontaneously became an electron and a positron. So branching curves means like that, something like that. From the list of particle tracks and assuming the same speed, the paths of the lighter and heavier charged particles are illustrated by tracks. Oh, okay, we've got a picture here. Oh, where's the picture? Where's the picture? There is no picture. Okay, this is horrible because I don't want to have to redo this entire video. Where is the picture? There is no picture. This is embarrassing. No, not on a huge scale, because as I said before, I'm just too old to be embarrassed by anything. So, okay, we'll come back to that question. Let's move on to the next one, which is, there we go. We have the information for this one. We have an analysis of a particle track within a magnetic field. And from the evidence of this particle track, the charge to mass ratio of the particle is, okay, so this is similar to the previous question we did. We've got the velocity, we've got the magnetic field strength, we've got the radius, and then it says the density of the bubble track suggests two elementary charges. So it could be +2 or it could be -2. It could have 2 excess electrons, or it could have be deficient 2 electrons. So the question is similar to the one we did before. You've got the velocity, you got the field strength, you got the radius. Change the put times 10 to the -3 for the radius because it's in millimeters. And again, that's a straightforward question. The answer is going to turn out to be C. This is the one which you have to think about a wee bit more. From the evidence in the analysis of the particle track, the particle is likely. What is it likely? So actually, you don't even have to think about that this much at all, because if it says the density of the bubble rack suggests 2 elementary charges, then what's it likely to be out of an alpha particle, a proton, a neutron, or electron? Well, certainly not a neutron. -1, +1, +2. There's your answer. All right. Well, that one wasn't as hard as I thought. Let's go on. Number 9. Maybe this one will be harder. A particle accelerator is used to accelerate protons to an energy of 4.5 mega electron volts, assuming the protons start from rest. What is the maximum speed reached by the protons? Okay, so if they start from rest, then this is just a kinetic energy question, isn't it? And this represents the kinetic energy. So it's EK equals 1/2 mv v squared, and we want the maximum speed, v equals 2ek over m square root. And all we have to do in this question is make sure we convert the kinetic energy, which is given to us in mega electron volts, into joules. So in this formula here, the energy must be in joules. You can't have it in electron volts. So that's going to be, we can do it separately if you want, or you can do it, you can put it into the equation. Let's just do it separately, because we know that 1 electron volt equals 1.6 times 10 to the negative 19. There we go. You could do it like that if you want. You say 1.6 times 10 to the negative 19 joules equals 1 electron volt. Then how many joules does 4.5 times 10 to the 6th electron volts? Once again, because that's mega electron volts. So if you do that, you end up getting 7.2 times 10 to the negative 13 joules. And once you have that value, you can plug it into the formula, multiply by 2, divided by the mass of a proton. And that will spit out the answer 2.9C. 2.9 times 10 to the 7. If you were guessing on that question, well, the only one you could eliminate really is D, because that's faster than the speed of light. The other ones, you could probably eliminate A, because when we talk about the acceleration of particles, subatomic particles, we usually talk about very high accelerations. Of course, that's possible. It's possible it could be going that speed, but chances are it's going to be going pretty fast. Number 10, determine the energy equivalent of the mass of an alpha particle. The energy equivalent. So this is where we start with formula E equals mc squared. And we want the answer. Remember that mass can also be expressed in these units, giga electron volts over c squared or mega electron volts over c squared. Anything electron volts over c squared is now a unit of mass. So all we need to know for this, so we're going to take this formula, all we need to know is the mass of an alpha particle, which is given to us. Multiply it by the speed of light squared, and we are going to get 5.9 85 times 10 to the negative 10 joules, which we then just need to convert to electron volts, or in this case, since all the answers are in giga electron volts, giga electron volts. So first do 2 electron volts. Divide by 1.6 times 10 to the negative 19. And that's going to give you 3.74 times 10 to the 9 electron volts. Which works out very nicely, because if it's times 10 to the 9, then it's already giga. So the answer is going to be C. Isn't it? Yes, it is. C. 3.7473 giga electron volts over c squared. Number 11. How are we doing? Oh, we're 15 minutes in. Maybe we'll... No, you know what? Let's just pound through this page here. According to quark theory, protons and neutrons are composed of easy peasy, up and down. Just a simple knowledge question. According to quark model, a proton, and again, just a knowledge question, 2 ups and a down. Remember, an up is positive 2/3 of the elementary charge, and a down is negative 1/3. So 2 ups and a down will make a total of positive 1 for a proton. A meson contains 2 quarks designated as an anti-up and a down. So an anti-up is going to be negative 2/3, and a down is negative 1/3. And if you add those together, you get negative 1. In beta negative decay, a proton changes into a neutron, a positron, and an antineutrino. Proton changes into neutron, positron, neutrino. Again, knowledge question. In beta negative decay, you start with a neutron, and it decays into a proton, an electron, and an antineutrino. All right, we'll stop there and continue with the next question in the next video.